So, morning everybody. This lecture, like every other lecture this semester, is likely to go beyond the time limit for the class, which is 9:20. So, what I intend to do is to stop the class at 9:20 and let those who want to leave, and I'll resume about five minutes later and complete whatever is left, just so that I can be done with today's topics today, right? So today we're going to begin our series of lectures on recurrent neural networks. So let me begin by asking you this a question. Here's a little bit of code. Can you see it, guys? Can you see it? Raise your hands, whatever,
Yep.
right? Okay, can you take a guess which project this comes from? Anyone?
What do you mean? Like C++? Like what?
No, it's some kind of, it's an open source project. Take a guess at what it could possibly be. Okay, now let it be, right? Yeah. Somebody's got
So I was going to say something with regards to law enforcement.
Bail. No, okay. This is actually, well, someone's got your microphone on, so please turn it off. Anyway, this looks like completely authentic code, doesn't it? Now, or here's something else. Here's a piece of math that looks like a Wikipedia page, complete with, here's a lemma, statement, there's a proof.
They're generated?
It's completely generated, right?
Yeah.
And here's a Wikipedia page explaining it all. Now, this of course doesn't make a lot of sense, but the amazing stuff is that all of this was completely blindly generated by a recurrent neural network. And what is impressive is the completeness of the generation. Now, look at this code. It has remembered every loop every open brace is closed. Everything is perfectly formatted. This was a neural network that was trained on Linux source code. And so the consistency of the code, look at this little loop where it's actually looping over the index I, and within the loop, it's actually reusing the variable that was being indexed within the for loop. So I is being incremented, I is being used for multiplication. It's not using some other character J over here. It opened, oh my God. So my PowerPoint has gone into spinny mode. But anyways, it opened a brace over here. It remembered to close it here. Every if block is properly indented. It remembers this code looks like something that was written by a professional. There are no mistakes, right? And it was produced by a dumb little neural network program. So, or this one. This was a network that was trained on technical papers, and it produced LaTeX code. Again, not only did it produce complete LaTeX code, meaning it kept track of the various things being opened and closed, it has semantic consistency. For example, there's a let's take this character C out here is consistently used throughout this little document, or this OX out here continues to persist all the way to the bottom. The entire thing is remarkably consistent. It looks like, and it even has a little figure to go with it, and the figure looks perfectly reasonable. If you squint at it just right, you could be fooled into believing this is a piece of math from a paper. Of course, things kind of break down over here, but this is not where the state of the art is. The reason I'm showing you these things is that the neural networks that produce these magical bits of generation, they were not particularly complex. There is it's all the code that was used to produce the stuff can be found on Andre Karpathy's GitHub page, where he talks about the unreasonable effectiveness of recurrent neural networks. He's actually paraphrasing Eugene Wigner, who grumbled about the unreasonable effectiveness of mathematics and explaining the natural world back in 1960. So, but the description fits. These things are remarkably good. And what you saw is not a very complex piece of code. I recommend that you all take a look at it, and you could play around with the code, and you'd be surprised at how well it does things like this. It's just that little bit of code, for example, trained on Linux source code. Of course, the state of the art is in text generation is that uses much more sophisticated models is actually way better. Like this one, right? One of the many sages of the time, the Bodhisattva Sakyamuni, was a popular religious figure in India and around the world. There are dates, 1575 until 1611. This Bodhisattva Buddha was said to have passed his life peacefully and joyfully without passion and anger. For over 20 years, he lived as a layman, observed the consistency with the dates, and dedicated himself towards the welfare, prosperity, and welfare of others, and so on. This looks like a little biography, and it's entirely randomly generated. You can actually go to the web page that generates these strings. I forget the web page, and you can type in some random characters, and it will build you a complete story. And it's just a random output by a network. So specifically, these are random outputs by recurrent neural networks. And so all of these are examples of modeling where in these examples we were learning to generate stuff, but more generally learning to analyze, produce, predict, and classify series data where we have many values arranged in a sequence, and the order in which they occur matters. So for example, something like this, right? Consider the problem of speech recognition. We have to analyze an entire speech signal or the sequence of spectral vectors derived from it, and we must recognize what was spoken. So the input is a sequence of vectors, and the output is a classification result for the sequence. Now, you need to see the entire sequence, which could be a varying length, before you make your prediction. Also, the order in which the inputs happen matters. You can't just flip a bunch of vectors and have it mean the same thing. The meaning would completely change. So also, text analysis. Now, look at this one. The Steelers, meanwhile, continue to struggle to make stops on defense. They've allowed on average 30 points a game and have shown no signs of improving anytime soon. This was a couple of years ago. Now, nowhere in this piece of text is the actual game mentioned. So imagine you're not a Pittsburgher and you're not familiar with the Steelers. You can't make out from this whether they're talking about football, basketball, soccer, baseball, or cricket. So you'd have to figure this out. And this is a text analysis problem. You must read the sequence of words and identify the topic and other information about it. Now, again, you have to read the entire sequence of words in the right order before you can take a decision. You can't just drop words and read them in random order. That would change the meaning. It could even make it meaningless. So this is a series modeling problem. And then you have the same thing in machine translation. The input would be a series of words in English, and the output must be a series of words in French. Again, this is a series modeling problem where the inputs come in a particular order, and you must consider the order in which the inputs come in before you make your predictions. Or, for example, if you're making predictions about the stock market, you consider the entire sequence of stock values from the past and make a prediction. So your prediction could be a scalar prediction. Should I invest in this particular stock or not? Or should I invest today or not? Or it could be a vector prediction. Which are the stocks that I can invest in today? Now, all of these are classification and prediction problems that involve series data, where we consider sequences of inputs and produce one or more outputs, possibly a single output, or even a sequence of outputs. Like in the case of stock market prediction, if you're a hedge fund manager, you have to make a decision every single day. So you're producing a sequence of outputs. And these are problems that can be cast as functions. And so obviously these can be done using neural networks. And what we are going to see is exactly how these things can be done using neural networks. Now, there's a little bit on representations. In all of the following slides, I'm going to use a simplified picture to show a neural network. Now, so far, when we drew neural networks, the way we drew them was something like this. We had a series of neurons, and then we had some other neurons over here, and we connected them up, etc., right? Now, this is basically looking at the network side on, or face on. You have the network in front of you, but then I can rotate the network, into the page, and then if you look at the same network from the side, all you're going to see is these 4 rows, and you'd have an arrow going up like so. But really, when you flip it back, this is what you would see. So I'm going to use this sideways view of the network in all of my illustrations. Did that make sense, guys? Did you understand what I mean by the sideways view?
Yes.
Okay. Raise your hands. I want to see, there are like 90 people in class. I want to see 50 hands raised. I also want to know why there are only 90 people in class. That's a different question. Okay. Right. So this could be the network. The figure is going to look like this. And this little arrow means that all of the neurons here are fully connected with all of the neurons here, which are fully connected with all of the neurons here. Now, the blue boxes generally represent inputs. So it's not neurons. These are just input vectors. So similarly, for example, if I had a network that was taking 2 different sets of inputs, then this would be the actual network, but the side-on view is going to be like this. Or if I had an input generating 1 layer of hidden representations, and then the next input generating and this hidden representation going into this layer of neurons, the sideways view is going to look like this. So this figure, every time you see a figure of this kind, you must actually imagine that it's something of this kind. So let me continue. So let's return to our series problems, stock market prediction problem. Stocks typically follow trends. So if you want to know if it's good to invest today, you want to look at how the stocks have been behaving for the past several days. Ideally, look at the entire history of stock values, but at least you want to look at what's been happening in the past week. So if I wanted to make a stock prediction today, can you guys suggest to me the kind of neural network, what kind of neural network would consider a bunch of stock values from the past to make a prediction for today? What would the structure be like? Anyone? Say I want to make a stock market prediction here. So, yeah.
Sorry, we have an answer. It's recurrent.
It's recurrent. Okay, recurrent is obviously I'm suppose I only want to look at the past 5 days. What would it be? Anyone?
There are also answers about could a 1D TDNN network work?
Thank you. Exactly. Right. That's what I'm looking for. So this is not 1D, is it? Is this 1D? This is yes, it's a 1D convolutional network, but the data are vectors. So I misunderstood what you were saying, but yes, here's a simple solution. I have a network that simply considers the stock values from today and the past several days. And so at each time t, it considers the stock values at t, t-1, t-2, t-3, and makes a prediction for the next day. And so this is how it would make its predictions. On each day, it's going to look at the current day and the past several days. Now, this is, of course, we're familiar with this. This is just a time delay neural network. Now, the network that we saw is a finite response system. What I mean by it is that at each time t, it takes as input the current and the past several inputs, xt through xt-n, and then makes its prediction yt. So anything that happens at any given time will influence the output from at time t until t plus n, and then afterwards it no longer influences the output. So let's visualize this to see what I mean. Consider some event that happened here at capital T. As the network is sliding by, making its predictions, this input is not going to influence the predictions until the network itself arrives at time t. And then, as you move ahead, it continues to influence predictions until this point. And once the window of inputs that's read by the network slides past t, this input no longer influences the output. So something that occurs today only affects the output for up to n days into the future, where n is the width of the input window that's considered by the network. That's 4 over here. So beyond that, the network does not respond to changes in x of t. So the amount of time for which the network responds to a change in the input is finite. So this is a finite response model. Now, if you want the network to consider longer periods of history, then the way to do it here is to explicitly increase the history considered by the network. Now, what would the problem with this kind of approach be? Anyone? Answers, guys? What would the problem with this approach be?
If you have like a large enough n, it can't take in small increments of time.
So the first thing is that's got to hit you is that as you keep looking further back, you're going to need more and more parameters, right? And so, yes, Grant? Okay, let me continue, right? Well, it's linear and in the length of the history. So you would think it's not such a big deal, but then the length of time for which you have to look back may be arbitrarily long. Consider the stock market, for instance. The stock market has daily trends. So what you're going to predict today, what happens today is clearly dependent on what happened yesterday. But it also has weekly trends. You get more trades on Monday because of the backup over the weekend. So this means that your window must be at least 7 long. But then you have monthly trends. People buy things right after they get their paycheck. So then maybe you want your window to be 30 days long. But then you have seasonal trends. And so maybe you want it to be 120 days long. But then you have annual trends. You know, market activity goes up every Thanksgiving and every Christmas. So in principle, now it's not just what happened the last Christmas that tells you about what's going to happen this Christmas. You're going to have to look at Christmases past for several years to get some idea of how the market is going to be this Christmas. Except nobody told you it's Christmas. You're going to have to figure this out yourself, that there is this kind of trend. So if you wanted to analyze the stock market and take all of history into account, you're going to have to look back several years, 650 days, in order to be able to make predictions about today. And in principle, you really want to be looking back, not just, for any finite amount of time. You want infinite memory. So you want an infinite response time. You need every prediction to be based on everything that happened in the past. Or alternately, you want something that happens today to influence the output of the network forever. These two are basically the same statement. And yet, you cannot have a structure of this kind because this is going to blow up the number of parameters. It's going to make the number of parameters infinite. So what we need is a model that has a finite number of parameters, and yet it considers the infinite past in making predictions. So we want a finite-sized, infinite response model. Did that make sense to everyone? Raise your hands if it did. I'll wait for 50 responses. I have 43 hands raised. So 7 more to go. Raise your hand if you got this. Okay, thank you. Rashmi, I believe there's a poll at this point.
Yeah, it's on the next slide. Should I launch it now?
Yeah.
Also lower your hands whenever you raise them. Otherwise, like I have to like manually do it.
So here are the poll guys. Okay, you have 5 seconds. Right, stop it. Okay, obviously, convolutional networks are, this is the poll for those who can't see it. So convolutional neural networks are, I have the wrong thing here, are not infinite response systems. A TDNN, as we saw, is a finite response system. And so for CNNs, an input at any time affects the output only for some time, the width of the analysis, the scanning MLP. After that, it no longer affects the output. So convolutional networks are not infinite response systems. What we want is infinite memory. So here's a very simple way of getting an infinite response system where something that happens today influences the output forever. And a simple way to do it is to simply feed the output at any time back into the network as input at the next time. So yt is some function of the current input xt and the previous output yt minus 1. Now, of course, for this to work, we would have to define yf minus 1. So because at time 0, you need some value for this yt minus 1, right? But then once that happens, what you observe is that if you have an output at some time 0, that is going to, if you have an input at time 0, that's going to produce an output. And then if you have no further inputs, just because of this y0 had some value and keeps going back into the network as y1, y2, y3, and so on, the network will continue to produce outputs forever. So this simple recursion gives you an infinite response system. A single input influences the output for the rest of time. Now, when a neural network has this kind of structure, where the output at any time feeds back as the input, it's called a NARX network, where NARX stands for nonlinear autoregressive network with exogenous inputs. Now, nonlinear because the net is nonlinear, autoregressive because it regresses on past outputs. It is self-referential. And the most generic form of such nets is where the output at any time depends on the past several inputs and the past several outputs the output at any time depends on all inputs, all infinite past inputs, and all infinite past outputs. Of course, you're never going to implement that. You'd have something much simpler. So here, here's an example of a one-tap NARX network that only takes the immediate past output as the input. So at any time t, the input is going to be xt and the output at yt minus 1. And so here's how this computation would proceed. At the first time, it's going to take this input, the previous output, compute the output here. Then you take a step forward, read in the next input, the previous output, compute something, and keep going forward in this manner. So at each time, the inputs to the net are the current input and the previous output. Now, here's a more complete representation that shows all the computations being performed. It shows every computation step. So look at what happens over here. If you have an input over here, you can just follow the arrows to see how it influences the output. This goes up here to this output, but then it comes back down here, influences this output and this output and this output and so on, all the way to the very end. So, and in each column, the input and the previous output is being processed sequentially by all of these layers till it produces the output. Now, again, you can see why an input at any time is going to continue to influence the output forever. Now here I've drawn the output separately as a yellow box. A more standard representation is to say that the output layer is going to have the value produced by the output layer goes in two directions, one out and the other as input to the next layer. And again, the flow of information stays directed. And so if you can follow the chain of arrows from any point to any other point, that shows you the influences. And you can see why an input at any time is going to influence the output at every possible future time. So this is an infinite response system. Now, this example is a one-tap NARX network where the output at any time depends only on the current input and the output at the immediate previous time. But you can generalize this. You can say that the output at any time depends on several past outputs and several past inputs. So you can say that yt is a function of xt through xt minus l and yt minus 1 through yt minus k. So this is a more generic version of the NARX network. And a complete NARX network, the theoretical model that was originally proposed, would in theory explicitly refer to all infinite past inputs and outputs. Now this is just a theoretical concept. Obviously, nobody's really going to implement this. What you're more likely to implement is something of this kind. Now, NARX networks are instances of recurrent networks. They're recurrent because the computation in the network at the current time affects future computations. And these have been very popular in time series prediction tasks like weather prediction, stock market prediction, and other phenomena where you have a distinct innovation process that affects the system. And so the NARX model allows the net to refer to the infinite past in making current predictions through the outputs. But then there's something mildly problematic about this model, in that the institutional memory, the memory of the past, is not in the network. The memory of the past is in the output produced by the network. The network itself never retains any memory of what happened in the past, and it's not explicitly referred to. So which means that what I mean by this is that as far as this network is concerned, the computation over here just got in some input. The computation over here just got in some input, which just happened to be the concatenation of this guy and this one, and just did its regular computation. There's nothing about the structure of the network that explicitly attempts to track memory. Whereas we want the network itself to have some internal structure that explicitly stores the past. So attempt one. Let's explicitly introduce a memory variable. And the job of the memory variable is to remember the past. That's it. So now we have this memory variable mt, which is a function of the previous memory, the hidden, and also other variables like the hidden states at the previous time and maybe the outputs at the previous time. And the hidden state at any time in the network is now a function not just of the input, but also what was remembered through the memory variable. And the output is a function of the hidden state. So this was actually the very first attempt at explicitly introducing memory into these networks. And let's look at a couple of variants, some models that use this structure. The first one was Michael Jordan's network called Jordan Networks. Michael Jordan is the guy who invented latent Dirichlet allocation. But this paper was, I think, his PhD thesis, 1986. And the paper was serial order, a parallel distributed processing approach. In Jordan's model, the memory is stored by this memory unit that simply retains a running average of past outputs. So instead of having just one output going to the network, this one retained a running average of all past outputs. So the value of this memory neuron at any time was mu times the value of the memory at the previous time plus the most recent output. Now, In his model, the input itself is assumed to be fixed. It's called a plan, and the objective is to train the network to produce a specific output for a given input. But anyway, the main bit over here is that this memory. The memory unit has fixed structure. It doesn't learn how to compose its memory. This is just a fixed, recurrent, running average of past outputs. So when you train such a network, the network is going to learn these weights. It's even going to learn this weight, but there is no training of the weights that connect into the memory neuron itself. So back propagation stops right here. There's nothing propagated beyond this, which means that even though you perform the entire computation as far as backprop is concerned, you would just be considering each of these modules independently. Now, so there's no explicit reference again to the states within the network. All we did was that in saying, instead of keeping all the institutional memory in the output, let me introduce a neuron in the network which stores the output, which doesn't make a lot of sense. So let's try to make a slightly different version of it, and that was this Elman network. Now, this was the one that Scott Fahlman mentioned in his talk last week. Now, Elman networks also use memory neurons. This was produced by Jeff Elman in 1990. Now, here you have a separate memory state called the context unit. And this context unit is different from the output. In this model, however, all the memory unit does is to clone the hidden state at the previous time. So it just copies it over as is. That's what is meant by this arrow with the weight 1. And this clone state is what is fed in to the hidden state at the next time. And so because the memory unit simply copies the hidden state over at each time, this is actually like many independent computations, one per time instant. Again, there is no back propagation going past this point. During the forward pass, it copies it over. So during back prop, you would be updating these weights and this weight, but then the derivatives would not be going past this guy. So which means that as far as training is concerned, once you've done the forward pass, you could have just sliced out each block of these and just done a regular training like an MLP. So although you have recurrence over here in that there's stuff in the network that retains information about the past, the recurrent behavior itself is fixed. It's just copying of the hidden state. And the training algorithm doesn't explicitly refer to the future when it updates parameters at the current time. So because there's nothing being passed back over here, when you're computing gradients over here, you would not be looking at what happened in the future. And so here's the story so far. Yep, there's a poem.
So we also had a question, and a student was asking, are these blocks that we talked about in the last slides identical to each other?
Yeah, every column is identical to every other column, right? Okay, 5 seconds. For those who cannot see the poll, that's these two questions. And so these memory neuron networks do not have true recurrence. Why is that? They don't have true recurrence because when you go back, when you're training the network, the derivatives that you compute out here do not refer to what happened in the future. So basically, and nor are these derivatives passed to the previous time instant, which means that every computation of derivatives is local to the time. It neither passes information backwards nor refers to the future. So this is not true recurrence. On the other hand, they do have, these networks do explicitly have a unit in the network to store memory. So here's the story so far. in time series analysis, models must look at past inputs along with current inputs. And looking at a finite horizon of past inputs gives us a convolutional network. Looking into the infinite past requires recursion. NARX networks recurs by feeding back the output to the input, and then they feed back a finite horizon of outputs. Simple recurrent networks include Jordan networks, which maintain a running average of past outputs in a memory unit, or Elman networks that store hidden unit values for one-time instant, just one-time instant in a context unit. And they're simple or partially recurrent because during learning the current error does not actually propagate to the past. So they're blocked. The back propagation is blocked at the memory units for both Jordan and Elman networks. But then the Elman network gives us a hint of what you could be doing. And this is actually a simpler and actually a better model for recurrence. And this is the state space model. If you're an electrical engineer or if you work with control systems, you're familiar with this model. Here we define a state variable ht, which holds the internal state of the network at any time. And the state variable itself is computed recursively through the state equation, where the state at time t is a function of the input at time t and the state at time t minus 1. Now, for this recursion to work, of course, we need to define the initial state h minus 1. And the state summarizes information about the entire past because it's self-referential. So the state at any time carries information about the current input, but also the state of the past time. The output itself at any time simply depends on the state at the current time. So this is what we will call a fully recurrent network, or we'll simply call it a recurrent neural network, but implicit is this full nature of the recurrence. So here is the neural network version of the state space model. The upper figure shows the basic calculations. The green box shows the portion of the network that represents the hidden state. At any time t, h of t is computed from the input at that time and the hidden state at the previous time, ht minus 1. The brown box shows the output layer of the network, which computes yt, the output, from the hidden state. And this lower figure shows the entire computation for a series of inputs. So every column is identical. And as we process the input sequentially, at each time, we compute the hidden state from the input at that time and also the hidden state at the previous time. So for the first time instant, of course, we don't have a previous time. So this hf minus 1 has to be defined somehow. This must be initialized. But once you do this, this recurrence is fairly straightforward. And again, you can follow the arrows and you can see that an input at time 0 is going to continue to influence the output at every time in the future. So this is an infinite response system. Now, although I showed the state variable with just a single box in the previous slide, you mustn't take this to mean that the state variable is just a single hidden layer. In fact, the state can be arbitrarily complex with any number of hidden layers. So you could have a state of this kind. Here, the state portion of the network actually has 3 layers. The only requirement we have is that regardless of the complexity of the state, we must define the initial values for the state to enable us to compute the output of the network at the initial time instant. So if the state has three sublayers, then h minus 1 must be defined for every one of these guys. So here is an RNN with a single hidden layer in its state. Now the green box represents a layer, and we have to define h of minus 1. Yeah.
We had a question about what's the advantage of having the memory rather than just looking at the previous output.
So they are the point was that when you just the state itself, the computation of the state itself doesn't have any self-reference to it. So in that manner, there's no clear advantage to this. If you're just looking at the output, The output is going to store some value, and that's about it. But the point is that the network, there's nothing in the structure of the model that explicitly represents recurrence. And so the assumption there was that you need something in the structure of the model that captures recurrence. And once you actually make the transition from saying, the output stores everything to there's something in the structure of the model that captures recurrence, then you can complexify the nature of the recurrence that we will capture, as we will see in the next several lectures. Whereas if the only way in which you're actually getting the memory is through the output, that flexibility is lost. So that's the key piece. That's about it. Functionally, there's no difference between the output and a hidden state. Does that make sense? So whoever raised that question, yes or no? Oh, wait. So did they reply, guys?
Yes, they said thank you.
All right. Okay. So 53. Yeah, this is the slide we ran, right? Okay. Now, so here is an RNN with a single hidden layer. And here the green box represents a layer. And we have to define the initial state for that one layer. And the figure shows the entire computation for a series of inputs. Every column is identical to every other column. And to answer the previous question, just being able to do this means that now I can build a network of this kind where the recurrent net layer now has, the hidden state has two layers. And this is obviously far more complex than just feeding the output back in, right? And so now, again, because I have two layers, we have to define initial values for both of these layers. And again, continuing on the same theme, here's a network with a more complex hidden state with two layers. This hidden state still has only two layers, but the connectivity is more complex. So yeah.
We've also gotten a couple of questions about what's the connection between these and hidden Markov models?
So hidden Markov models are generative models. They're going to have some similar structure of this kind when you draw the structure, but these are not hidden Markov models. These are not generative models. There is no distribution associated with these. It's just very deterministic computation. Right?
Diksha, there's also, Chris has raised his hand.
Mm-hmm. What is the question, Chris?
Right. So with the, oh, geez, hold on.
Okay, you can either mute yourself or yeah, go ahead.
Yeah. So with regards to the formula that you gave for computing the hidden state, you talked about the fact that the hidden state is a function of the current input and the previous hidden state. But I was wondering, how does this relate to memory in terms of infinite response? Because we're only looking at the current input and we're not looking at past responses.
So here, this is the actual computation now, right? Or in a more complex model, right? So what happens? If I have an input over here, it influences the hidden state at the current time, which influences the hidden state at the next time, and so on forever. And so it influences the output forever as well.
Oh, right. Okay, that makes sense.
Right? So the distinction between just feeding the output back in and having a hidden state is the ability to complexify the model, but that's about it. But this just adds this infinite response to the model. Now, and here's a more complex one. We just saw this, more complex architecture. Or you can even, or there's something even more complex like this guy here. Or you can even feed the output back in to the network. And now this begins to look like a far more complex version of the NARX network, right? So you can see why this generalizes the notion of a NARX network. The hidden state actually gives you a much greater degree of flexibility in how you will learn your to retain memory. Now, also, The network is not restricted to looking back at only one time instant. One or more layers of this network could look back at more than one time instant, in which case you're going to have to initialize, you're going to have to define your initial values such that you can validly compute the output at the first time instant, which means here, for example, if it's looking at two past values, you're going to have to define h-1 and h-2 for the second layer of this network. So you can see how the whole thing works as a general idea, how recurrence works. The most popular structures, though, are the simple ones, like this one right here. They generally get the job done. They're simpler in terms of implementation and computation. Now, often when we draw the recurrent networks, we won't draw the full unrolled figure like these. Instead, we will use simpler illustrations like this one. So the figure will only show just one column of the input with a little looping connection. Now, this looping connection is not meant to imply that the output feeds right back to itself at the same time. This is the recurrence. So it means that the output at any time feeds back as input at the next time. And so we have different kinds of recurrence over here. Here, the hidden state has two layers, and each of those layers feeds back to itself at the next time. Here, again, the hidden state has two layers, and each layer gets an input from so the first hidden layer gets an input from the input and itself at the previous time. The second layer reads in the output of the first layer and the input and itself at the previous time, and so on. But the point is that this little loop over here just represents recurrence. So here is the first model. This has just one hidden layer with recurrence. So the full computation is shown by this figure over here. Of course, we have to define h-1. Or this model, these two loops actually represent the horizontal flows shown in this figure. So this recurrence represents this series of connections. This recurrence represents this series of connections. The point being that every column is identical to every other column, and each hidden state is obtaining inputs from itself at the previous time, as shown by this little recurrence over here. Or if you have this model here, again, you can see how this is the expansion of the figure here. So again, this looping connection means that there is recurrence over time. And again, here we have to define the hidden state values for both layers. Now, this clear to everybody? Raise your hands if it is. And wait till 50 hands are raised, only 30. Thank you. Right. I have to bully my way through these classes, otherwise you tend to fall asleep, and so do I. Now, let's look at the actual computation of these networks. So let's consider, for example, this network with just one hidden layer in its state. So here, the way the h value, the hidden layer, is computed, you first compute an affine function of the input and the hidden state at the previous time, and then finally compute an activation of this affine function. So there are two sets of weights. The superscript 1 means that over here represents the set of weights that the layer takes from the input. The superscript 1 represents the weights from the same layer at the previous time. And so you can see that at any time t, it combines and computes an affine function of the inputs at time t and the hidden state at time t-1. The output, of course, is just an affine function of the hidden state at time t. And so the output is an activation of an affine function of the hidden state at time t. Here's the more complex model. This one, you have two hidden states in the in the state. You have two hidden layers in the state. So for the first hidden layer, you compute an affine function of the inputs at time t and the same hidden state at time t minus 1. It's affine, so you also have this bias. And the parameters are these weights and the bias. So you have the current weights connecting to the input. You have the recurrent weights connecting to itself at the previous time and the bias. And of course, there's an activation function that applies on to this affine function. Now, after activation, that acts on this affine function. For the second hidden state computes an affine function of the output of the first hidden state at the same time. So at time t, for the second hidden state, you compute an affine function of the first hidden state at time t and the second hidden state at time t minus 1. So this is the recurrence. So again, this has two sets of weights. One is the current set of weights connecting to the lower layer, and there's the recurrent set of weights connecting to itself at the previous time. And then finally, of course, there's an activation that applies on this affine function. The output, first you compute an affine function here of the hidden state at the same time, and then you apply an activation. So you see how these things work. Same thing here. This is slightly more complex, but then it's the same thing. For the first hidden state, you have compute an affine function of the input at the same time and the state itself at the previous time, and then you apply an activation. The second layer first computes an affine function of the first hidden layer at the same time. And because of this arrow over here, the input at the same time, and then finally the recurrent through this recurrent connection of the same layer at the previous time. So again, there are two kinds of weights over here: the current weights, which connect downwards to other layers below the current layer, and the recurrent weights, which connect to the previous time. This is the distinction I really wanted to make. Now, the questions, is this clear? The distinction between, yeah.
Sorry, there's a question about what does the subscript represent? So like I, J, K, could you?
Okay, so this one, instead of using the matrix matrix version of the equation, I've just sort of written it out in scalar form. So remember that you have this box actually represents a bunch of neurons out here, right? This box also represents a bunch of neurons out here. So HI1, or consider this, HI2 is the ith neuron in this set at time t. That is computed by applying a function, the activation for that neuron, over this term. And here, you're computing the set of weights from all of the neurons at this time to the ith neuron in this layer, plus and the set of weights from all of the inputs to the ith neuron of this layer, and the set of weights from all of the neurons at the same layer at the previous time to the ith neuron in the same layer. So this is explicitly just writing out the individual weights instead of writing it as a matrix. Did that make sense? Whoever raised your hand. So Rashmi, what they say? So Ravni, that's a question?
Yeah, so they understood it.
Okay, got it. All right. Okay, so in the figures so far, we've shown one version of a recurrent net where you get a series of inputs, and at each time you get an output. In fact, you can have many variants to the structure. This is the simplest one, where each input produces an independent output. There's no recurrence. This is just an MLP. Or you can have something like this, where a single input produces a sequence of outputs. This is what we'd have for sequence generation. For example, if we input an image and output a caption to the image. So a single input produces a sequence of words. Or we could have a series of inputs and a single output. This is what we have for speech recognition or text classification. You see the entire text and you decide its category. Or you can have a delayed sequence-to-sequence model where the entire input is read and then an entire sequence of outputs is produced. This is what we'd have for machine translation. You see the entire English text, you produce the entire French text. And then, of course, you can have the regular many-to-many model where at each time you get an input and produce an output. So this is what we did for stock prediction, for instance. And this model over here is in some sense the most generic of all of the models we've seen. So over here and in the rest of today's class and in future lectures, I'll sort of continue to assume this final model. So here's the story so far. Time series analysis must consider past inputs along with current input. They must look into the infinite past, and that requires recursion. NARX networks achieve this by feeding back the output to the input. Simple recurrent networks maintain separate memory or context units to retain some information about the past, but during learning, the current error does not influence the past. State space models retain information about the past through recurrent hidden states. So these are fully recurrent networks. The hidden initial values for these hidden states must be specified, and usually these are learnable parameters. These can actually be treated as learnable parameters. And here in state space models, they enable the current error to update parameters in the past as well. So here's where we are so far. Now, how do we train these networks? To train these networks, we'll employ a technique called backpropagation through time, or BPTT. So our training data will now consist of input-output pairs, where the input is not just a vector, but a time series, and the output is also a time series. So in response to the input sequence, the network will produce an output sequence, and that output sequence must be made to match this desired output sequence. So this is the most generic setting, and we have to train, again, all of these columns are identical, and we have to train the parameters of this network such that the actual output sequence matches the desired output sequence most closely. Again, we are speaking of sequences, not of individual outputs. You want the input sequence, the output sequence to match the desired output sequence. So again, it's kind of important to note over here that this unrolled network is just one giant neural network with shared parameters. All of these columns are identical. So we're going to train the network using gradient descent. And because this is just one giant neural network, as in all neural networks, you will start at the end and then you will propagate the gradient backwards. But the end over here happens to be the final time, and backwards happens to be going backwards in time, which is why we will call this back propagation through time. Now, to compute the gradient, we are going to first perform a forward pass, where for each input, we'll pass the input sequence through the recurrent network and generate a sequence of outputs. So here's the pseudocode for the forward pass or the inference. At each time, you'd go through the hidden layer. You can assume that the 0th hidden layer is the input. You'd go through the hidden layers, and for each hidden layer, first you compute this affine value, which is a weighted sum of the hidden layer at the previous time, the hidden layer, the same hidden layer at the previous time, the previous hidden layer at the current time, and the bias. So this HT L-1 is the same hidden layer at the previous time. No, sorry, the lower layer at the same time. HT-1L is the same layer at the previous time and the bias. And then finally, you compute the hidden state value by applying an activation. And then once you're done with all of the hidden layers, you're going to compute an affine value from the final hidden layer and apply an output activation to compute the output of the network at that time. and this computation happens at each time. So this is assuming the time synchronous model we just saw. Now we have to compute gradients for the gradient descent rule using the gradient descent rule, and we're going to use backpropagation. Now again, this is just one giant neural network with shared parameters. Every column is identical to every other column. So this means we're going to have to use the rules for shared parameter networks to compute the gradients and perform gradient descent. Now I'm going to sort of change the diagram a little bit. Instead of having this figure over here, which is maybe a little bit, doesn't quite represent what's going on, this figure seems to indicate that there are two distinct outputs, which is not the case. So just to ensure that you realize that it's the same output both going up and going sideways, and to ensure that you realize that the inputs are all going in from the bottom, I've sort of changed the figure to have these little S-shaped curves. Nothing's changed. This is the same figure as this guy, just being a little more explicit in the illustration, right? Now, as the first step, we will compute the divergence between the actual sequence of outputs produced by the network and the desired sequence of outputs from the network. Now, this divergence is a scalar. It's a single number, but it's a function of two sequences. Now, the important thing again is that this is not just the sum of divergences at individual times. You're not going to say that my desired output has one output at each time. The actual output has one output at each time. I'm going to just compute the individual divergences and sum them up. That doesn't hold. For example, if you are performing speech recognition, the network may produce 5 words as an output, but the desired output may have 7 words. So you can't even find a one-to-one correspondence between the output and the input. You can't just decompose this divergence into the sum of divergences at individual times. It can be a much more complex function of two sequences. And so what we really must consider when we train these networks is the general case where the divergence is actually a function of two sequences. It's the error between sequences. And we'll see how this complicates matters in later lectures. So let me just pick some notation. Our inputs are xt. The desired output is this sequence dt. I'm going to assume for now that, just for convenience, that the desired output indeed does have one output at each time, but this is not necessary again, right? This is just for the purpose of illustration. So in that case, I'm going to have as many outputs as inputs. The network will have one output at each time. And so that's shown by this y of t. And at each time, as you perform the computation for each layer, here I'm going to assume just one hidden layer, but this will generalize. You first compute the affine value at the input to the layer. Then you apply the activation and compute the output to the layer. Then you compute the affine value at the input to the output layer, and then you compute the output of the output layer. So the superscript 1 represents the Z superscript 1 represents the affine value at the hidden layer, first hidden layer. H of t is the hidden state. Here I have only one hidden layer. Z superscript 2 is the affine value at the output layer, and y of t is the output of the output layer, right? This is just the notation. And I'm going to be representing the weights in this manner. So W superscript 1 represents the weights from the input to the hidden layer. W superscript 1 represents the weights for this recurrent connection. W superscript 2 represents the weights from the hidden layer to the output. Okay, so we've just sort of set up all of the variables for the math. I won't actually explicitly chant out the variables when I explain this in the lecture, but this is for your reference. The slides are fairly detailed. So now, as the first step of back propagation through time, we are going to compute the derivative of the divergence. Again, remember this is the divergence between two sequences. And we're going to compute the derivative of this divergence with respect to the final output of the network, yt. Now we're going to assume that although this divergence is a function of two sequences, it is possible to compute the derivative of the divergence with respect to each of the outputs of the network. This is going to be required, right? And this can actually be a source of significant difficulty in many scenarios, computing the derivative of this divergence with respect to these individual outputs. But for now, we're going to assume that it's just possible, right? And so now there's a special case for the divergence, where the divergence between the output of the network and the desired output can be sort of decomposed into divergences at individual times. This is not the generic case, but there are in some very special cases, we can assume that there is a desired output at each time and there's an actual output at each time. And you can compute the divergence between these two and sum up all of these divergences. And the sum represents the divergence between the two sequences, the sequence of outputs and the sequence of desired outputs. In this case, the derivative of this total divergence with respect to an individual output is simply the derivative of the local divergence with respect to that output. But this is not the generic case, right? Now, this would happen, for example, if you were doing stock market prediction. Each day you make some prediction, you make some error. So you could just sum up the errors over all the days. But if you were doing machine translation or speech recognition, this is not going to hold. So now, in the first step of the backprop, ignore the slides at the bottom. The equations in yellow will focus on the vector notation. We already have the derivative of the divergence with respect to the output at the final time. We can propagate it backward by multiplying that by the Jacobian of the output layer to compute the derivative with respect to the affine value at the final time. Then we can propagate that backwards and compute the derivative with respect to the output of the hidden layer at the final time by simply multiplying the derivative with respect to Z2 by this weights matrix. This is just a standard backpropagation like we did for MLPs. And now we can also compute the derivative with respect to the weights over here, which is simply going to be h of t times the derivative with respect to the affine value over here. So h of t times the derivative of the divergence with respect to Z2 at t. Now this again is just like your standard MLP. And you can also extend this to include a bias by adding an extra one. I won't go into the details of that because the math is fairly straightforward. And you can verify that the divergences work out. The dimensions work out. And now I can take a step back and compute the derivative with respect to the affine value of the hidden layer, which is Z1 of t. And for that, I just post multiply the derivative for ht by the Jacobian of the activation function over here. And now I can compute the derivatives for the weight matrix at the input, which is simply going to be x of t times the derivative with respect to Z1 of t. And now I can also move backwards and compute the derivative with respect to this recurrent connection, which is now going to be the product of the hidden layer output at this time and the derivative of the divergence with respect to the affine value at this time. So now you're multiplying two terms on either side of a recurrent connection. But that will give you the derivative with respect to these weights. So far, so good. This is just like a standard NLP, nothing fancy, right? And I can continue here. Now I go back in time. I have the derivative of the divergence with respect to the output here. I can propagate that back and compute the derivative with respect to the affine value at the hidden layer. And here's the first change between your standard MLP and the recurrent network. the output of this layer went to two places. It went up to this output layer. It also went forward into the same layer at the next time. So the derivative of the divergence with respect to the output of the hidden layer at time t minus 1 is the sum of two terms. The first is the derivative of the divergence, the derivative at the for the affine term here times this weight matrix plus the derivative of the affine term for the affine term here times this weight matrix. So you actually have a sum of two terms. That's change number one. Change number two. Now I can continue going backwards, and I can compute the derivative with respect to this weight, which is going to be the output here times the derivative for this affine term here. But now this weight was the same as the weight out here, right? So I'm not computing an independent derivative out here. In fact, I'm adding the derivative that I computed at time t minus 1 to the derivative value that I've already stored computing, that was computed over here. So the derivative of the divergence with respect to W2 was first computed here, and now I'm adding to it as a plus equals ht minus 1 times the derivative for z2t minus 1. So did you guys understand why there's a summation out here? How this happened? Raise your hand if you got that. Any questions on chat?
Yes, we do have one. So is there a limit to how many time steps that can be allocated while implementing this backprop structure?
It's going to be as long as the input itself, right? So only 21 people understood what I was saying. All right. This is either people aren't paying attention or they aren't getting it. So what happened to the remaining 75 of you? Did you get it or did you not?
I have a quick question, Dr.
Yeah.
Bhatia.
Mm-hmm.
So it looks like we're updating the weights between updating the weights of the recurrent hidden states, like the weights that connects the hidden states to each other.
Mm-hmm.
So when we go through time, we add these perturbations, these derivatives.
Correct.
But then it looks like, let's say at xt plus 1. I think I got it.
All right,
Yeah.
fine. So
yeah, thank you.
guys, have you got it? Raise your hands. I want to see 50 hands raised. Otherwise, I'll wait. $46. I need two more. Thank you. Be so kind, right? So you can see how these derivatives keep getting updated. So now I can sort of propagate it back, compute the derivative here using the same rule as before. But now when I compute the derivative for this weight, again, I'm doing an increment because I've already computed it out here because it's a shared parameter network. And then when I compute the derivative for this guy, again, I'm doing an increment because it's a shared parameter network. And then I can compute the, go down here and continue, basically repeat the operations that I performed here on this column and on every column going backwards, all the way to the beginning of time. And then there's one final step. I can also compute the derivative for the hidden state at time minus 1. And the hidden state at time minus 1 is often treated as a parameter to be learned. And so I can also use this derivative to perform gradient descent learning of the initial value for the hidden state. What is the best initial value for the hidden state? So here is the complete backprop algorithm. You're going to initialize all derivatives to 0. Then initially you compute the derivative of the divergence with respect to all of these outputs. And then as you go back in time, you just go compute the various derivatives, the outputs, the derivatives to the affine values and the derivatives for the weights, and increment them appropriately. I won't go over this. This is just sort of laying out what we saw in more detail on the slides back there. So there are some hands raised. Any questions? Okay.
Yeah, Professor, I have a question.
Yeah.
So, like, if the time step is very long, like infinity, and as we back propagate to the time ends at 0 or -1, will the derivative be infinity since it's accumulate all the previous derivative?
So if you had infinite time, the accumulation would expect you would expect it to blow up, but you never really deal with infinite time. So long as you have other issues where things can blow up even for finite time, and we'll deal with this in the next class. But your inputs are generally finite, so they won't blow up to infinity through simple summation. That's almost never going to happen.
Okay, thank you.
Right? And so
I have another question.
Yeah, go ahead.
Is divergence computed only at the end of the sequence, or is it done at every step of generation?
So the divergence, once you're done with the output, the divergence is between two sequences. So you know, in most cases, you cannot compute it incrementally.
Okay, it's only at the very end. Thank you.
Yeah, because I mean, there are situations where it's an incremental sign, but it's a sum of divergences at individual times. In that case, you could be computing it incrementally, right? But then even that doesn't mean that you can perform backprop, because even though you computed the divergence over here, the derivative for this term really requires the derivatives backpropagated from the end. So you're going to have to wait till everything is computed.
Okay, thank you.
Make sense?
Yes.
Okay. And so there's a pseudocode for the backpropagation through time. I'll leave it to you guys to go through it. It's very straightforward. It's really very simple. It's literally just doing what I just showed you in the slides, right? So, and of course, this procedure that we saw can be generalized to any recurrent architecture. We'll see some specific cases in future lectures. Rashmi, is there a poll over here?
Yeah, it's at 105. So
Start it here. Right now. Wait, which is
oh wait, I can read.
Yeah, go ahead. Poll 3, right? Backprop, yes. There's a poll, guys. Can you see the poll? Nobody's responding. Yes. That's this one for slide 97.
So we have a question. Why don't we directly propagate Z instead of H? Any motivation?
Just hang on. Let this poll be done. So stop the poll. Only 56 people have voted. What happens to the rest of you guys? Are you asleep at the gate or something at your computer? This is, please don't, you know, it's kind of bad. You take a lot of effort to wake up at 8 in the morning and come to class, and then you just, you know, splonk yourself or begin staring at email or whatever else is not right. It's a waste of your time and mine. Okay.
Bhiksha, I see a lot of private messages saying they don't see the poll, so maybe they did not really see the poll.
Why didn't they see the poll?
Sometimes there's like a Zoom issue, so they have to like leave and rejoin. That has happened to me as well.
All right. Anyways, so what was the question?
So the question was, why don't we directly propagate Z instead of H? Is there any motivation?
So what I hear, if you're propagating Z over here is the equivalent of just adding an arrow directly from the input to this guy, is it not? Or out here. So that's going to become, that's the same as having a linear activation. if I were to draw it, if I were to propagate Z, if this is my activation F, and this is my activation F, what you're really suggesting is that you compute the Z value over here and compute the Z value over here. So this is like having a recurrence with linear activation at this point. It's a perfectly valid thing to be doing. It's a linear system. You're losing the non-linearity of the recurrence. And in fact, when we analyze things in the next class, that's what we're going to look at. It's a good question. It's a very nice question. Did that answer your question?
Yeah, the student said it does.
Yeah. Was there another question?
Yeah, I actually have a question for that same graph, like
yeah,
this one. So from here, I see that the divergence is a function of all of these outputs. Like in the vanilla MLP, we had one output, and if we had like shared parameters, we would update them, but then those parameters would affect the final divergence. So here, after back propagating all of these weights, we kind of like change the output of the earlier time steps, right?
So the point is that you don't, I mean, remember, once you're done back propagating it, you're going to be running a forward all over again, right? So you had a forward, and then you back propagated everything, and then you updated your weights, and then you're going to run a forward. You're going to unroll the network all over again.
Oh, okay. So that's going to be a lot of computation.
It is.
Okay.
I mean, but it's no different than your MLP, right?
Yeah,
Even if you were doing an MLP,
yeah.
you'd be computing this all over the place.
In
terms of computation, there's no extra computation.
Yeah, I see. Thank you.
Except the matrix multiplies. Yeah. Any other questions, guys? So Rashmi, can you stop the recording briefly?
Yeah, sure.
Just stop it.